Okay, so thanks a lot. Thanks for the invitation and the opportunity to be here. I guess I'm the Dutch touch to this mathematical festival in honor of Emmanuel. And actually, I'm old enough, and I was lucky enough to be there when it started. So in '95, I was a finishing master student in the Netherlands, and I was attending my first conference in which I didn't understand anything. But at the end, Oort handed out a sheet with the open problems and open questions that he thought were interesting. And one of them was what is now known as the Andreatta-Oort conjecture. And at the time, Oort had two students working on this already, Rutger Noot, the first one, and then there was Ben Monen, who sort of were working on characterizing special Shimura subvarieties from the differential point of view as a totally geodesic subvarieties, and from sort of p-adic point of view as a translation of formal tori in Caraiani coordinates for around ordinary points, okay, at least for AG, the moduli space of principally polarized abelian varieties. And I think Bas was one of the referee of Ben Monen's thesis, so he picked up the problem. And he developed what Gregorio described as one of the pillars of in the work around Andreatta-Oort. Then the French school kicked in, so Emmanuel and Bruno. And then new ideas came in, so the Pilat-Zanier method, O-minimality, and great work of, among others, Zimmermann. And then the last stage for at least one of the proofs of unconditional proofs of Andreatta-Oort was in which I was involved was related to the Coulomb program, and the tool used there was p-adic Hodge theory, okay, that allowed to solve this average Colmetz conjecture that Zimmermann used to get an unconditional proof of Andreatta-Oort for Hodge-type Shimura varieties, and then the story continues. But I'll stop there. So that was 2015, so many years had passed, 20 years. And being old, actually, it's nice to look back and see this common effort of mathematicians, different angles on which you approach the problem, different techniques, different ideas, which I think makes our mathematical world wonderful, right? It's a community all over the world, right, in this moment where there are divisions and tangents and so on, that all work in sort of in the same direction, and I like it a lot. Okay, so I think one of the driving forces, at least in this saga, Andreatta-Oort and around Andreatta-Oort that I witnessed, I think it was Emmanuel. First of all, for the mathematics he did, but also for what someone mentioned already the last few days. It has the fact that it was really able to get people involved, started collaborations. For example, I think the Dutch and French communities had shared students, they had lots of interactions, and I think Emmanuel was really behind that. Jian Gao here is one of the examples. And thanks for this. Thanks for being one of the actors of this saga. Okay, so when I started preparing for this, I was wondering what to talk about, and since I'm the Dutch touch, I decided to bring it to mod P, characteristic P geometry, which I think was one of the main themes of Franz Oort mathematics, and from which he also got inspiration to think about Andreatta-Oort. Okay. So I'll try that's why I chose this specific topic. And I want to do it recasting some questions in terms of some sort of mod P algebraic geometry. So we know that around in the Andreatta-Oort business, algebraic geometry is very important. So you have a Shimura variety over in characteristic over C. Okay, you have the uniformizing Hermitian symmetric space that embeds in its compact dual, and the two extremes of this almost triangle. Okay, the Shimura variety and the compact dual have an algebraic structure, and special subvarieties are really characterized having shadows, both as an algebraic subvariety in the compact dual, as an algebraic subvariety of the Shimura variety. Okay, and now we learned in the beautiful lecture by Mingyai Zhang on Monday that a similar picture exists now thanks to work of Scholze and Caraiani Scholze in mixed characteristic 0p. And using exactly the same framework, I want to phrase a question I cared about a lot, and I think also Franz Oort would like it. Okay, so let's fix some notation to start. So P is an odd prime, and actually for second theorem I will need, I hope I will remember to add this assumption, I will need also P bigger or equal to 5, and we fix S to be an integral canonical model in mixed characteristic 0p of a Hodge type Shimura variety well, maybe yes, the D was the Hermitian symmetric space, G is the reductive group over Q defining it, and we assume it has good reduction at P. Okay, and we also fix of the dimension D, and well, we sort of will need at some point some smooth toroidal compactification. We know it exists these days in the Hodge type setting, and I assume it's I've already localized and completed the reflex field over which this is defined. So this will be an unramified extension of Q. So it's the completion of the ring of integers of the reflex field at a prime or at a place over P. And then to this we attached, I still have to attach some few data. So the fact that it has good reduction in particular implies an effect that our algebraic group calligraphic G has a reductive model over ZP.
So you assume this is unramified?
Yes, yes. It comes in this good reduction assumption. Okay?
Good reduction over
yes.
over Z, or over the ring of fields, over the reflex.
So the definition of good reduction implies that the reflex field is unramified over Q.
Okay.
Okay. So GZP is a reductive model of G over ZP. And then the second assumption I'm not going to write is that the group K that I wrote there as defining the finite level Shimura variety at P is exactly the ZP points of this reductive group. Okay, that's also part of being of the good reduction assumption. And finally, I have the main actor, since we work in characteristic P, and have a Roman G, which is simply the reductive group that I get by passing to modulo P. And then, as we already seen a few times, over this completion of the reflex field, we also have a model in the conjugacy class of the Hodge co-character that is defined over WK. Okay, and then associated to this, we have P, which is P mu, which is a parabolic, associated to mu, and I will also denote by P minus the opposite parabolic, which is defined by the inverse co-character. Okay, and I think that's all what I need for the time being. So now I want to redraw the picture that was already on the blackboard in Mi-Yang Zhang lecture. And then we will specialize to the case of principally polarized Abelian varieties and see what it means, okay? And see maybe a few things.
I'm sorry, why do you obtain a projective model of G over ZP rather than over the completion corresponding to W?
That's also part of the being a good reduction. Okay, it's good reduction.
You want it to be
yes,
really over ZP?
To be over ZP,
Okay.
so that the P part of the compact open that defines the level structure is really the ZP points.
Okay, so unramified is not enough?
No. Okay, so we have, from Monday's lecture, so we have seen that we have the following picture. So I have my integral canonical model. I can take the rigid analytic fiber, okay, which I denote Sn, and then on Monday it was explained to us that one gets a certain perfectoid space. It's perfectoid if you go to CP, but that's also fine. You can also base chain to CP. And this should really be thought of as some Galois, infinite Galois cover. As I said, we will see what it means over AG. And then for AG, then we have pi Hodge-Tate, which is the Hodge-Tate period map, which goes, so it goes to this quotient. So here we have the opposite parabolic. Again, I need to take the analytic fiber. These maybe I will also denote as some flag variety for G U minus. And then here I can take a specialization map since I fixed a compactification of S. So maybe let me write here S0, S sigma 0 special fiber over K of the data that I fixed there. And here also I have my G, I have my P minus, let me write simply again P minus instead of P minus K and so on. So it's some specialization map. So if I'm consistent with putting 0 at the special fiber, I have this other flag variety. And so this should really be, so with the complex numbers, this is the Shimura variety, this is the Hermitian symmetric space, and this is sort of the analogy of the compact dual. The map is not injective, as we said. And the theme of my lecture is really to try to compare a bit the geometry of these two spaces via this common roof. Okay, so on the left-hand side we have what is called the EO stratification. So EO is for Ekedhal-Oort. On the right-hand side we have Deligne Lusztig stratification. So both use the fact that we are in characteristic P, so there's a Frobenius, which you use to stratify these two spaces. And I really want to compare this stratification and this stratification when I pull them back to this perfectoid space. And before I say more about this, in fact, I will continue, then I will complete this picture on this blackboard, so leave some space if you take notes. And maybe I want to do an example. And the example is the case where I have as S AG, which is the moduli of principally polarized abelian varieties of dimension G, possibly to avoid problems with some prime to P lattice structure, which is really a moduli space. Okay, and then in order to describe also the compact dual, actually, let me fix V to be ZP to the 2G with its standard symplectic form. And then, at least on CP points, we can describe the diagram as follows. So if, say, I fix A over OCP, a principally polarized abelian scheme, and then well, not sure it fits here, but let's try. So I have the modular points, which certainly defines a CP point of my moduli. Okay, and here actually to fix a point. Actually, let me omit this. It's simply a CP point. So to give a point over A, over it simply means that I fix A and I fix a symplectic iso between TP A dual over CP and V. Maybe it's not readable. Let me use the other blackboard. So I have my moduli point here, and to fix a point over it, it's simply A plus an eta. Okay, so this is the p-adic Tate module, say, of the generic fiber, and this should be symplectic. Okay, and then here this flag variety. So this classifies G-dimensional isotropic subspaces in V, okay? And the point that I get here, so this goes here, and then via the pi Hodge-Tate map, well, I can do the following. I can take the map. There is a map which was already well known and studied by Fontaine, which is this D-log map. Which goes to the invariant differentials of A, say, over CP. Hope everyone can read, not really. So we have this map. Is it readable now? Okay, good. So this is actually a surjective map.
So it goes from to the, what is WA?
This omega is the invariant differentials. so this the map d log, and well, I can associate this. So wait, so this is isomorphic to V tensor ZP via by my eta, okay, and I can simply take the kernel, so the corresponding point. Maybe I'll write it here. I simply take the kernel of the induced map from V tensor ZP to omega A. Okay, this is so this is surjective. This is rank 2G. This is rank G, and you get something which is isotropic and G-dimensional. So very nice thing. In fact, if you look at the construction of this map D log by Fontaine, you will see that this map is even rational. Okay, it is integral. Sorry. So I really have a map of OCP modules, which is not surjective in general. So it's if and only if A is ordinary. But still, if you want to understand what is the point in characteristic P that you get in this way, you take the kernel of this map. This is an OCP submodule of rank G. And then you reduce, right, modulo the maximal ideal of OCP, and you get the FP bar point here that is given by this picture. So it's not difficult, right? So the nice thing that Scholze and Caraiani-Scholze allowed is really to sort of globalize this local construction that we knew. Okay. Okay, so I want to speak about, so that's I hope that in the case of AG this is less mysterious, okay. So the point here, since I've chosen my A to be an abelian scheme over OCP, it's simply the specialization modulo the maximal ideal of OCP. And you also see why we had to get a well-defined specialization map and have this toroidal compactification, because maybe your abelian variety over CP will be an extension over OCP, whose special fiber is not an abelian variety anymore. It could be a semi-abelian scheme, and then you need this, so you could go to the boundary when you specialize. Okay, so what can we say about this stratification? In this, in this setting, okay. So we need to add the two arrows here, but for the moment, let me say something about this stratification before I say how they are constructed. Okay, so so I fixed, given my group G, maybe passing to not over FP, but say over a larger field. If I fix a Borel and a torus with the property that they are contained in P, so I can define the Weil group of G, and then inside it I have the subgroup generated by the simple reflections fixing the Levy defined by P. And then if I take the quotient, so this is simply a set, but actually there is a preferred subset of representatives of this quotient, which is given by the constant representatives. So oh, sorry, I want to do this, I think. Yeah, I think so. So in every class in this quotient, there is a unique element in here of minimal length. Okay, so this gives a representative. And then the Ekedahl Oort stratification in this more general setting of Hodge-type Shimura varieties are indexed exactly by the elements in this constant representative. Which I denote EOW. And on the right-hand side, I do the same, but instead of taking this parabolic, I take the opposite parabolic. So these are the constant representative for W modulo WP minus. So this is again the value group defined by the type of P minus. And again, for every W in P minus, we have a strata. Okay, and and in fact, one remark is that in fact the cardinality of these two sets are the same. So that's really intriguing. You have two things here which have the same number of stratification, and you wonder, are they in any way related one to the other? And I decided that instead of maybe going too much into technicalities, I'll give you two examples, or maybe, yeah, I hope three, but I see that I'm already a bit behind. Okay, so one example, it's quite easy. It's the case of AG, and I start with the G equal 1. Okay, then the strata. So this so this S sigma 0. This is simply a modular curve, and then you know that the natural way to stratify this is super singular or ordinary elliptic curves, and then the cusps are always ordinary. So here are the two strata. And then I have the ordinary ones. And then instead this flag variety, it's simply a P1, and then you have elements in P1 FP and the complement. And you wonder what happens if you sort of draw this roof that we have there, and you go up and down. Okay. Okay. So let's look back, because ordinary points we understand very well where they go, using this integral version of the log. Okay. Because in this case, so this p-Tate module of A dual is the p-Tate module of the p-divisible group. Okay, it doesn't really change. And then if you look at the p-divisible group of an abelian scheme which has ordinary reduction, you know that you have this connected Ekedhal Oort sequence. So inside TP A dual, even before tensoring with OCP, you have the p-Tate module of the connected part, the multiplicative part. And this goes to 0, okay, via the map D log. So you have a G-dimensional subspace already defined via this isomorphism in V. So which means that if you do this construction and you take the corresponding filtration modulo P, you get an FP rational point. So the ordinary points get maps to P1 FP. Okay? And in general, the So the ordinary locus, thanks to this property, will always go, in the case of AG, to the FP rational points of this flag variety. In this case, maybe I should have said the parabolic group P that you fix is the standard Siegel subgroup. It's defined over ZP. So the flag varieties, when you reduce it modulo P, it's defined over FP. And via this explanation, all ordinary points goes to the FP rational points of this thing. And now instead, if you take all the things that go to the supersingular points, okay, and you map it down, you get everything. Okay, so there is some bizarre phenomenon. So it's not as nice as we maybe might thought, that via this correspondence one stratification goes to the other stratification. There is some relation. The relation seems to flip the dimensions. That's the first thing that we get. Okay, but it certainly doesn't preserve the strata, simply because, for example, as I said, supersingular elliptic curves.
So in this picture, when you say P1, you say the point of P1 in some ring or in some...
Yeah, so the variety, I consider the variety, the scheme P1 over FP. Yes. Yeah, it's far up. So just add a phi p on downstairs. Okay, let's see a second example. G equal 2. I had also an example with the Hilbert-von-Blumenthal varieties, but I'm not sure we'll get there. Okay, so let's study the special fiber of. So in this case, S is equal to A2. And let's consider S0. So I don't want to define the Ekedhal-Oort stratifications on this toroidal compactification, but it's not difficult. It's simply defined in terms of the Ekedhal-Oort stratification of the sort of the abelian part of the degenerating abelian varieties. Let's consider this. Okay, and we sort out the strata by dimension. So we know that there is an open dense thing, which is the ordinary locus. And then a first filtration that we have on characteristic P abelian varieties is the P rank. Okay, so you know that if you have a two-dimensional abelian variety, you take the P torsion, you take the FP bar points. So this is an FP vector space of a dimension between 0 and 2. So the ordinary case is dimension 2, but you could have something of a dimension 1. So this is of dimension 3. So you have this this divisor, and then the P rank 0 instead, so you don't have any physical point in the P torsion. And in this case, you know that your abelian variety is isogenous to a product of supersingular elliptic curves. But it can be, so we have a refinement because it can be isogenous to a product actually of the same supersingular elliptic curve, or isomorphic. In this case, it's super special. And if I really want to get a strata, I should really omit the super special point. So here means that, yeah, okay. So your abelian variety is really isomorphic, of course not with the polarization, but as an abelian variety to a self-product of an elliptic curve. Okay, so let's see instead this flag.
So does it depend on which supersingular? I think I was told it's not, but I don't. So if something is a product of super singular elliptic curve, there are several of them.
Yes.
In higher dimension, is it the case that all those products are isomorphic?
Yes. 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 It is.
Okay. Isomorphic without the polarization.
Without the polarization, yeah. So if you want to classify them, then you really have to say how you put the polarization on this.
Excuse me, there are associated parabolics here, according to your definition. So what are they?
Yeah, this is, yeah, no, because so there is no, so it's really in a moduli space. So this is not a flag variety. It's not an homogeneous space. Okay. So it's not immediately clear what is the relation between the group G and there is one. There is a relation. Okay. I'm going to say this in a second. Yes. Okay. So this classifies. We said W, which are subspaces inside. Say I'm considering FP bar points inside, which are isotropic of dimension 2. But here you see you have a Frobenius coming from the fact that this V is defined over ZP. You can simply apply the identity tensor Frobenius. So you have a Frobenius isomorphism on this space, and now the Deligne Lusztig variety simply measures how the subspace that you start with is in relative position to its image under Frobenius. Okay, so you see that you have two extreme cases. Okay, and I sort them out by codimension. So codimension 3. I prefer to do it by codimension because this correspondence, as you've seen already in G equal 1, sends dimension to codimension, so I prefer to do it this way. So these are the zero-dimensional locus. This is the case where W is sent to itself via Frobenius, so it's defined already over FP. And you have finitely many of those. Then you have a second possibility is that so the intersection between W and its transform under Frobenius is of dimension 1. Okay, but here again you have a refinement. So it could be that this intersection is defined over FP or not. Okay, and this actually is so here you have the intersection FP is over dimension 1. So you get a subvariety of dimension 1, and actually it's quite clear what you get, because here you get already a line in V tensor ZP FP bar. You take the orthogonal, that's a three-dimensional space, and to get all the W's with this given intersection, you simply have to take a vector in this quotient of this three-dimensional space by W, which is a line in a FP bar vector space of dimension 2. It's a P1. So you have a bunch of P1s. Okay, very easy to describe. And then you have the possibility that this intersection is of dimension 1, but not FP rational. And then you have the generic case when the intersection is 0. So again, the number of strata are the same. And so this stratum, we are already proving for you, that goes to this stratum. Okay. Now this stratum, you have a P rank 1. It means that, well, maybe you don't have a kernel of this map for your abelian variety that defined rationally on V that goes to 0, but you have a line at least. Okay. So you see that this thing here go, well, not to here, but to the closure of the stratum. Again, using the canonical subgroup, you can prove that you go beyond. Of this stratum. Okay? And for the others, we don't know. Okay? Okay, so.
You don't know, but you expect.
I have a theorem. So the theorem says something. Okay, so actually there is one way. So in order to define this stratification, so I will forget the real multiplication locus, which is actually fun because it's the case where the flag variety we are considering is defined over not over FP, because it's not split. It's not a split case, but I don't have time. Okay, so the way that nowadays these Ekedhal-Oort stratification are defined is actually given through two maps. To a certain stack. Actually, yes, GK, sorry. So these are certain quotient stacks. I'm not sure I will be able to define this group acting on this. It's cooked up actually by the parabolic we started with to come to your question. Okay, so you take the here you take the parabolic and its opposite parabolic twisted by Frobenius, and you put them together to act on GK. And here instead you take the opposite parabolic and it's transformed by Frobenius, and you put them together to act on GK. And here there is a story. So let me describe some properties, and then hopefully, well, I'm not sure I will be able to say much. Okay, so the story goes as follows. So these quotient stacks were defined by Pink, Vedder, and Ziegler. It's the theory of G-zips defined. And actually they are nice because so you are able to define the strata not only pointwise, but you really give a scheme structure. So it's important to have such a map. And this really extends combinatorial work of Oort and Monen and Wieman-Monen, etc. So in the case of AG, the Ekedahl-Oort stratification beyond the case G equal 2 is defined as follows. You put together in the same stratum a billion varieties with isomorphic p torsion together with the polarization. Again, this is a pointwise definition, but this has a scheme structure. And there is a combinatorics in terms of the H1 Ram homology and Frobenius and Verschiebung, how they behave to classify this p torsion subgroup schemes that is packaged inside this this quotient stack. And two.
So which stratification does it give you when you fix the type of just the p torsion subgroup as a group scheme? What kind of?
You get the Ekedhal-Oort stratification on AG.
Okay.
Yeah. Second, so this map ZEO was defined by Xiao Zhang, on former student of mine, and in an invention paper by Goldring and Koskivirta on S0 sigma. And now I can state the first theorem, which is due to my student on S0 and to myself on this smooth audio compactification, is that this map is actually smooth. And as a corollary, so you have the following, okay? So maybe first let me define the following. So there is a topological space underlying this quotient stack, and this is actually naturally in bijection with this constant representatives. Okay, so now you take a W in here, and then so you have this topological space with this well, definition, maybe remark. And now if you take the Ekedhal-Oort stratification associated to W, it's simply the inverse image of this corresponding sublobes.
Can you show again the map?
Sorry?
Can you show again the map GEO on the
It's a zeta. It's a zeta. So it's a zeta.
zeta.
Yes.
Thank you.
Sorry. Sorry. It's this map here.
Okay.
Okay. And in particular, as a corollary, we get that each Ekedhal stratum is smooth of dimension the length of W if non-empty. Okay, so there is this result of smoothness allows to describe this, and also actually this quotient space in this work of Pink, Baron, Ziegler. So this is a finite set, and there is an order relation defined by closure, okay, defined by this topological space, and this is completely determined by Pink, Baron, Ziegler in terms of the Weil group. Okay, so it's a purely combinatorial description, and this is exactly thanks to this the fact that the map is smooth, so it's generalizing. So the closure relation that you have on this finite set, okay, gives exactly the closure relation between the Ekedhal-Oort strata. So given one stratum, you take the closure, you know what is in the boundary. It's again a union of Ekedhal-Oort strata, and this is defined purely combinatorial. Okay.
So dimension, it means pure dimension, or usually it's connected also.
Well, I mean, it's equidimensional.
Yeah, okay.
It's equidimensional. Which was, when I was a PhD student, actually it was one of the main activities of Oort, to already in AG, to determine what is in the closure of what. So this is and let me advertise further work on this. So there are other consequences of this smoothness. First of all, Goldring and Koskivirta worked out sort of a theory of automorphic line bundles on this stack. They studied this, and as a consequence, they pulling it back via this map. Okay, so it's similar to what we saw yesterday. So this purely combinatorial thing, it's easier to study, and pulling back the results, you gets a theory of partial Hasse invariance on 0 sigma, and they apply to reobtain results of Scholze. In the case of good reduction Shimura varieties, it has the construction of torsion Galois representation associated to classes in coherent cohomology. Which for AG had been worked out also by George Boxer. But so the combinatorics of this space is very useful, and the automorphic theory on this nice finite topological space is very rich. And also using this map, Vedern and Ziegler, and using also this automorphic theory, in fact, characterized Studi the tautological ring of S0 and S0 sigma. So they prove that the subring generated by Chern classes of automorphic vector bundles, they are, it coincides with the subring defined by the classes of the Ekedhal-Oort strata, for example. Okay, and they deduce, for example, what we saw yesterday, the vanishing of Chern classes of flat vector bundles in characteristic 0 using this, so giving a new proof of this result. So it's that's to say it's a very rich map, this one. Okay.
Can you say what's the dimension of this that star GK mod ZEO?
So this is it's really the topological space. It's a finite set of points. Right. Okay. So the dimension. I think it's D, the same as the dimension of the Shimura variety you started with. Yes. Yes. Okay. So let me then give a second theorem that wants to describe a little bit the relation between this strata and this strata here, and the result is the following: that there exists an involutive order reversing bijection sigma 0. Here the ordering is really this ordering that I told you about, that describes the closure relation in the Ekedhal-Oort stratification, while here the ordering that you fix is the ordering given by the Deligne Lusztig part. By the way, the analog of this theorem 1 for this map, it's quite classical. So in fact it's smooth, so you also get as a corollary, but this also was well known, that the strata are smooth of a given dimension, with the property first of all, for every W, the length of the image is the dimension of the Shimura variety minus the length of W. So there's a swap. Remember that the dimension of the Ekedhal-Oort strata is the length of this Weil element. There is a swap in the dimension when you apply this thing, and if you assume that
what does it mean in projective here, because it's not from the same thing?
No, I mean if yeah, sorry, yes, yeah, you're right. Thanks. Yes, absolutely. So if you assume that if you take so let me denote by so this is Q1 and this is Q2. If you assume that these intersect a given stratum. So you take the inverse image and you pull it down of a certain Ekedahl stratum. You intersect with the Deligne Lusztig stratum. You suppose it's non-empty. Then W prime is less or equal in the Deligne Lusztig order to sigma 0 of W. Okay. Which means, for example, if you look here, right? So it really tells you that the images of a certain stratum via this correspondence, okay, it really lies in the closure of the corresponding stratum given by the image of W under sigma 0. Okay, so it tells you some closure relation. So here, for example, as we said, supersingular points where you have something where the length is 0 goes to the closure of something which has dimension now 1, which is everything. Okay, so it gives some weak explanation of what happens.
So in case of AG, W is a symmetric group or?
So in the case of AG, so the cardinality of this VP is 2 to the G. Okay.
For which P?
The Siegel parabolic in this case, yes. The Siegel parabolic, yes. Okay, and my time is over, but I maybe want to say something because I think there is a lot of algebraic geometry that we need to understand. So in fact, the way one proves this result is to prove that there is a correspondence. So this is a really nice scheme. So there is a correspondence dominating these two nice smooth spaces, okay, which is defined as follows. So I have my thing here on the blackboard, you see. So if you want to study that map modulo P, you don't really need, in the case of AG, the full map D log, okay? So you need this map D log modulo power of P with the property that I told you that is not surjective, but you really want a power of P so that the corank of the image of this into this can be understood, okay? And in fact, P cubed is enough. So to construct that S tilde, what you do, you take the moduli space of abelian varieties. In characteristic 0, you take full level 3 structure, and then you take the normalization of the model, step 1. Step 2, so the Fleck variety really classifies isotropic subspaces, okay? So already, if you instead working over OCP, you work over some normal base, like this model that I told you about with the normalization. So you have a rank 2 G module, a rank G module that generically are isomorphic, but it's not true that the image will be a rank G. So you need some blow-ups to make this work, okay? So the second ingredient to construct this S tilde, beside this normalization, is this blowing up, so that this property holds. And then what happens at this level is that, so here you blow up to have this extra property of having images of vector bundles which are still vector bundles, and these are blow down, okay? So it's a nice correspondence that I learned in a paper by Piloni and Stroh. So there is, so the key ingredient to prove this result is really understanding this diagram. Of course, we just get a weak result because in the process of defining S tilde, you have this normalization that we know very well. It's a nice, easy process to define, but it's completely impossible to describe explicitly in high dimension. Okay, I really wanted to define this, but I see I have no time, so I'll stop here.
Questions?
What does the theorem say about the missing cases in genus 2?
It says that so if you take something of dimension I, you take the corresponding simply this. So you take the image under sigma 0, and it lies in the closure. So so in that case, there is really, since the strata are ordered essentially by dimension, there's a precise match. So the stratum of dimension I goes to the closure of a stratum of codimension I. Yeah.
So basically, as you just said, your theorem says that like when you map the EO strata to the Deligne Lusztig one, the image will lie in the closure of the Deligne Lusztig one. Do you have examples on like you're missing certain things, or like what's the expectation?
No. So I don't know if, for example, I don't know if everything in the closure can be obtained this way. I don't know. Yeah, one nice thing that, so except for very special cases, for example, if this is the W is the identity element, then we know. And in fact, we also get, I should have mentioned this as a corollary, a result which was expected, that but not known yet, that these Ekedhal-Oort strata are non-empty. Okay, so you get similar results, but precise control of what happens, no, I don't have it, and I don't really have examples at hand. Yes.
Okay, if there's no more questions, we will resume at 10 to 11.